Hi, we are the group number 7 participating in IEOR Graduate Research Initiative under the guidance of Professor Yuri Faenza. Our project is Algorithms for Matching Markets. I am Cody and my teammates are Joanne and Weihang. The structure of our presentation is as follows. I will walk through the background of our project and the first model. Joanne will talk about our experiment, and Weihang will introduce our model 2 and property. Matching markets is a term from matching theory of economics. In such a market, both sides choose and must be chosen. You cannot just choose what you want, even if you can afford it. You also must be chosen. In our project, we focus on the application of some algorithms to the course registration process. In a typical course registration setting, there are always high-demand courses that cannot accommodate all students, so we want to find a relatively fair way to allocate. There may be required courses to complete, and of course, some courses take place in the same time slot, and students can only pick one from them. Our objective is to introduce a model that takes semi-core requirement and class overlap into account, propose ways of creating preference lists, and develop an algorithm for assignment and test on each preference list. I'm going to talk about our semi-core model. We are given a set of students capital S, and each student S needs to take Q sub S courses. A set of courses capital C. For each course C, it has a capacity Q sub C. We also have a set capital C prime, which includes all semi-core courses in capital C. A partition of capital C into sets C sub 1, C sub 2 to C sub k, where all classes in one set take place at the same time. We want to find a fair matching capital M that satisfies course capacities, semi-core requirement, and resolves time conflict.
We propose 4 different methods to create preference lists for our model. The first method uses a lottery to represent each course's preference of students. Course prefers whoever appears sooner in the lottery. This is similar to our university's course registration process. In the second method, each student is given a positive bid endowment to allocate across the courses. We assume students bids higher on preferred course, and courses prefer students with higher bids. However, Sonmez and Onver pointed out that preference inferred from bidding cannot reflect students' true preference. To test this, we also directly ask students for their preference on courses in the third method. Lastly, to take into account that students' bids may be influenced by time slot clashes, we allow students to bid on time slots instead of courses. In other words, the same bid entered for both courses in the same time slot. This method also directly asks students for their preference on courses. We modify the Gale-Shapley algorithm as follows for our model. The algorithm first assigns one semi-core course to each student to fulfill their semi-core requirement. Students propose to their favorite semi-core course, and each course rejects students based on course preference and course capacity. As soon as everyone satisfies their requirement, the algorithm assigns the rest of courses to them in a similar way.
Upon formulating our model and algorithm, we designed an experiment to test the 4 different methods of creating preference lists. To carry out this experiment, we emailed our peers from the IEOR department and enlisted their help to fill in a course selection form based on a hypothetical setup. In our setup, participants were given 8 different courses, indexed from C1 to C8, and were tasked to register for 3 of them. In the experiment, we used the names of 8 real IEOR courses. The participants were then given the following information. Firstly, they were informed of the course's historical demand. Secondly, each participant must enroll in at least one class from the semi-core group. Lastly, participants were provided with a timetable of course timings, where they can enroll in at most one course per time slot. We divided our participants into two groups and provided them with slightly different instructions. For Group 1, we asked participants to bid on the 8 different courses, keeping in mind that a higher bid gives them a better chance of success. We also asked for their course preferences, but explicitly informed them that we will not consider their preferences during allocation. For Group 2, we asked participants to rank the 8 different courses and bid for the courses and time slots. Participants were informed that course bids and time bids were 2 different methods of allocation, and their preferences will be taken into account. To evaluate our course allocation, we consider average ranks, where 0 refers to a most preferred course and 7 refers to a least preferred course. Student average rank, which is the average rank of a student's assigned courses, is used to assess individual student outcomes between different methods, while the test average rank, which is the average rank of all students in a test, is used as an aggregate metric for the performance of different methods. Results. Comparing course bids only to course bids with preferences, we see improvements in test average rank for both Group 1 and Group 2. This improvement is more significant for Group 2, where students were informed that their preferences mattered. Accordingly, 36% of students in Group 1 and 54% of students in Group 2 experienced improvement in average ranks. Comparing first-come, first-served to bids and preferences, we also saw improvements in test average rank for both groups. Interestingly, we saw that course bids and preferences led to a slightly greater improvement than time bids and preferences. We also saw that using bids and preferences now led to some students having worse outcomes than in the first-come, first-served condition. This is because they may have initially gotten lucky under the first-come, first-served condition. However, we conclude that the benefits outweigh the costs, as more than 71% and 85% of students experience an improvement, compared to 14% and 4% of students who experienced worse outcomes.
Similar to the outcome of other matching algorithms, our outputs also have some special properties. Imagine in an assignment, courses alpha and beta are assigned to student A and B, respectively, and A prefers beta, B prefers alpha. While it's feasible to allocate alpha to B and beta to A, we certainly do not want this to occur. In contrast, we want our output to be semi-core stable. We define this property by 5 statements for each student and course. Semi-core stability suggests a relatively fairness of the matching. In our experiment, the output of our test 3 and 4 are semi-core stable.
In conclusion, first, when considering semi-core requirements and lower lapse in schedule, bids plus preference is a better and fairer method, giving semi-core stable assignments. Secondly, we lose stability compared to students' true preference when we use bids only or first come, first serve. Third, while more tests are needed, our algorithm seems to provide a promising alternative to the status quo. Thank you for listening.